So there are three types of intermolecular forces. These are also called van der Waals forces. And we'll just go slow. The first type is called dispersion forces. Now think about these electrons in these molecules. Okay, so the electrons are kind of arranged around the molecule. And suppose for one split second, all the electrons in this first molecule kind of gather at this end of the molecule. So now you have this end of the molecule being a little bit more negative than that end. So we put a little delta minus, a little delta plus. So what happens then? This creates an uneven electron arrangement in the molecule. And now this next molecule is close by. And what do you think this next molecule is going to do? This molecule has like what we call an instantaneous temporary dipole. Suddenly for one split second all these electrons are on this side. Then the neighboring molecule, its electrons kind of feel this effect. So what do you think these electrons are going to do in the neighboring molecule? They are going to run away. So really the electrons from the neighboring molecule do not want to be close to the electrons to this molecule, right? Because they're both negative. So what the neighboring molecule does is it creates an induced dipole. Basically, it forces the first molecule, it forces this second molecule to create this arrangement where the electrons again are on one side versus the other. So you have this dipole, the delta plus and delta minus now show up in the second molecule. This attraction between the molecules, between the negative side of one molecule and the positive side of the other, is what we call the London force, or the dispersion force, because it kind of just happens as the molecules are moving around, the electrons are moving around in the molecules. So then it propagates. The third molecule feels the effect of the dipole, this instantaneous dipole in the second molecule, and those electrons in the third molecule run away over to the right hand side, and these ones should be on the right hand side, and they feel this attractive force where there's less molecules, less electrons in that molecule. So this attraction between this temporary dipoles in these compounds is called the London dispersion force. It's very temporary, it's relatively weak, but for nonpolar molecules this is the main attractive force. So what happens to the molecule that experiences London forces? Well, basically we have the ability of a molecule to do that really depends on the size of the atom and other factors, and we call that the polarizability. How an atom is able to form its electron cloud so I can give these little dipole-dipole attractions. So how does the size of the atom affect the London forces? Well, the smaller the atom, the weaker the forces. Basically, if you have a small atom, it's like a marble. It's very hard because the electrons are quite close to the nucleus, and so they don't really want to move around that much. So smaller atoms are more like marbles. They don't have that strong of attractive force because they don't move around as much. Larger atoms, on the other hand, are what we call soft, easily deformed like cotton balls, mostly because if you have larger atoms, the electrons on the outside are farther away from the nucleus, therefore they're more likely to move around and have that mobility. So the polarizability is greater in larger atoms. And a good example of this is comparing helium to xenon. We're comparing non-polar compounds. This is where the forces are actually significant. So if I think of helium being small, it's kind of got a very definitive boundary here. And as we get larger out to xenon, the boundary is a little bit more fuzzy because these electrons can start to move around the atom more because they're so much farther away from the nucleus. They're not close to the protons. So as the atoms get larger, you have more stickiness, more of that increased London force attraction. How does that affect properties? Well, if you have greater attraction between the forces, these particles will tend to stick together more, and it takes more energy to pull them away to go into the vapor phase from the liquid. So in terms of boiling point, this has an increase in the boiling point as you go down from helium to xenon. So if you can understand that, hopefully you can answer this question too.